Hello students, welcome to EPG Pathshala. I am Sunil Kumar from IIT Delhi. Today we are going to talk on module Introduction to Optics from the paper by Basic Biophysics. In this paper, we will learn about the following things. In the first one, we will address the issue of the question, what is light? Why do you see things? How light is helpful in seeing things? Basic properties of light. Then light as electromagnetic waves. Optical phenomena where the wave nature of light is used to explain phenomena like reflection, refraction, interference, and diffraction. We also discuss about the quantum nature of light and discuss some optical phenomena where the quantum nature of light is essential to explain them. And those optical phenomena are, for example, scattering and photoelectric effect. We also will discuss the basic optical components which are used in optical instrumentation, such as mirrors, lenses, cameras, etc. Optics is a branch of physics in which we not only learn about light and related optical phenomena, but also devise applications where light is used. In the broadest sense, electromagnetic waves are just another form of energy that is different from those we had known so far. The credit of revealing the wave nature of light goes to James Clerk Maxwell. He showed that a beam of light is superposed wave of electric and magnetic fields. In this module, we are going to learn about light or electromagnetic waves in general and the photon nature of light. We will have a closer look at things or optical phenomena that either you had known already or will be seeing someday in future. Note that there are various interesting topics in optics which have not been discussed here. However, at various places in the module, the interested readers have been referred to the literature available at other sources which they can use to learn more about particular topics. Let's start with a basic concept with light. That is, how do we see things? Light that we see is simply one form of energy that the sun or any other light source emits. Our eyes sense it and help us in seeing the world around us. There are two ways that light can enter your eyes. First, there could be a light source like a light bulb or any other light source that you see in your houses. This light then travels into your eyes and your brain interprets this signal as light. The other way, which is more common, is to see things by the light reflected or scattered from them. So what is reflection of light and scattering of light? These concepts we'll learn a little later, but these are the two ways which help us in seeing things around us. Now let's see what is darkness. How do you define darkness? How dark is your room? That is the basic question. So darkness is something which is always relative. It's not that you can quantify the amount of darkness that is present in your room or in some place. If you are in a room that is completely dark, what would you see? What happens after you wait for a long time? This is the question which is asked generally to everybody in the audience, that if the room is completely dark, would you still be able to see people around you if you wait for a little longer? After some time, your eyes could adjust and then you will be able to see something around you. So the idea is that darkness is always a relative thing. There are always, if we can say in terms of photons, light present at any place. Basic properties of light. So here we kind of summarize the basic properties of light. The first one is, and the most fundamental is, light travels in a straight path. That is, while traveling from one point to another in space or between objects, it takes a path which has the minimum path length, and that is a straight path. The second point is, light can propagate through vacuum or any medium. Meaning, if light can be considered as waves, then these are the waves which do not need the presence of a medium to propagate from one place to another. So light waves or light can propagate through vacuum or any other medium. The difference is that in the media, some of the light gets absorbed, some gets reflected, and some gets transmitted. Other common properties of light can be color, wavelength, wave number, frequency, energy, power, intensity, etc. So first of all, if light can propagate through space, what is the speed of light? So in vacuum, it has been found that the speed of light, which is a universal constant, is the highest, and that is 3 into 10 to the power 8 meter per second. Light is characterized by a quantity called wavelength, frequency, wave number, and it carries a specific amount of energy that depends on the wavelength. It carries a spectral power, which is the total power per unit wavelength. And then there is another thing called polarization, which also is used to characterize light, which basically is the direction of the electric field vector. Reflection and refraction of light. So these are the properties, or these are the phenomena which can be understood by using the ray properties of light, meaning that you assume that light is like rays, and if these rays are incident on some surface or interface between two media, some of the rays get reflected and some get transmitted. So if the angle of incidence is theta I, the angle of reflection should also be theta I, and depending on the medium, the second medium, the angle from the normal of the transmitted ray, which is called refracted ray, is the angle of refraction, and the plane containing the incident ray, the diffracted ray, the normal to the surface, is called the plane of incidence. Snell's law. So for the reflection and refraction of light, we use Huygens principle, which basically states that any point on which light is incident acts like a secondary source of light, meaning that light is considered as waves, and any point on the subsurface acts like a source of secondary waves. For example, in this figure shown here, light waves are falling on the surface, and there is a wave front from one medium to another medium, propagating or moving with the speed of light. The wave front gets tilted in the second medium, and the amount of tilt depends on the refractive property or the refractive index of that medium. So the wave front in medium 1 in this picture is shown by a line AB, and that in medium 2 is shown by line CD. So if the angle of incidence was theta I and angle of refraction was theta R, then according to Snell's law, n1 times sine theta I should be equal to n2 times sine theta R, where n1 is the refractive index of medium 1 and n2 is refractive index of medium 2. Let's discuss something very interesting phenomena, which is these days used very very often, that is in optical fibers, and this property is called total internal reflection. This is about light reflection from an interface between two media which have a slight contrast in their refractive index. And this is actually one important consequence of the Snell's law of refraction. It says that for light propagating from a more dense medium to a less dense medium, such as shown in this picture here, meaning the refractive index N1 is greater than the refractive index N2, and therefore sin R, where R is the angle of refraction, is larger than sin I, where I is the angle of incidence. And because in this particular case the angle R is larger than angle I, so it's very easy to find a condition where R is equal to 90 degree or larger than 90 degree. So when the incident angle I is such that your refractive angle R is either 90 or larger than 90, the light remains in the same medium, it doesn't propagate to the other medium. So this property of light is called total internal refraction. For example, if you have an interface between air and glass, so glass has a refractive index of about 1.45 or so. So the light which is traveling through glass, for incident angles larger than critical angle, which happens to be around 42 degree, the light will just be confined in glass itself. And this special property is very much used in optical fibers, and these days they are used for optical communication, for example. Now let's talk about some optical elements which are used for guiding light or transporting light from one place to another, or for making use of light in imaging and applications like that. So mostly mirrors and lenses are the optical elements which are used for such purposes. And geometrical optics, meaning light assumed as collection of rays, is all about it. So for example, plane mirror, what does a plane mirror do? It is used to see images of objects which are not directly in your view. For example, in the image shown here, you have a mirror and you have some object and you are standing at a place that you are not able to see the object directly, but you are able to see the object through the mirror. So this imaging of the object through a plane mirror is simply, or can be understood simply by the optics called geometrical optics, where light is considered as collection of rays. Another optical element is curved mirror, which is used again in the similar fashion for imaging of objects. For example, in the image shown here, if an object is sitting at a distance P from the curved mirror, and curved mirror in this particular example is having a curvature which is spherical with radius of curvature capital R, let's assume, and a focal length small f. Let's say the image created by the curved mirror is at a distance small I from the mirror, then this equation has to be followed always, that is 1 upon P plus 1 upon I equals 1 upon F. So if you know the focal length of any curved mirror and you know how far the object is, or you know how far the image has been created by the mirror, you can calculate how far the object was or how far the image will be created, or vice versa. The other important optical element that is very often used in every optical instrument is a lens. A lens is nothing but is a piece of glass which has two surfaces, having a curvature. That curvature can be same or different, and because of the curvature, the way light gets refracted through that glass piece is such that you are able to image a point in the object plane to another point in the image plane. And the lens equation goes in the similar fashion what we had seen for a curved mirror, because curved mirror also had a curvature, and in the case of a lens, the two surfaces can have same or different curvatures. So here also we have the lens equation which goes as 1 upon p plus 1 upon I equals 1 upon f, where f is the effective focal length of the lens, p is the distance of the object from the lens, and I is the distance of the image created by the lens. For example, in the image shown here, the object placed at point O is imaged at point I by a very thin lens, and the imaging by the lens is very well understood or very well explained by geometrical optics, which is explained in the second figure here. And very often we see a simple lens in the form of hand lenses or used in cameras and so on. So the lenses can be of two types. One is of the convergent type and the second one is of the divergent type. In the first type, which is convergent lens, light coming from infinity, meaning that the light which is nearly parallel to the optical axis or the principal axis of the lens, after passing through the lens, passes through the focal point of the lens. In the second category, which is the divergent lens, light coming from infinity or light which is nearly parallel to the optical axis of the lens, after passing through the lens, appears to be coming from a point on the other side of the lens, and that point is at the focal length of the lens. So the light which passes through the lens appears to be diverging in this category, and in the first category, the light after the lens appears to be converging to a point, and that is the focal point for all the light which is nearly parallel to the optical axis or the principal axis of the lens. Now the lenses can be of various types. For example, shown here in the first image. Depending on the curvatures of the two surfaces, the lenses can be biconvex, meaning both the surfaces are curved towards outside, or the lens can be plano-convex, meaning one surface is plane, the other surface is curved towards outside, or a lens can be convex-concave, meaning one surface is convex type and the other surface is concave type. The lens can be of meniscus as shown here, or it can be a plano-concave, or lenses can be of biconcave type. Depending on the applications or depending on the kind of application you have in mind, you can choose any one of these. Then you have compound lenses, meaning not necessarily you have to use a single lens for any application. You can have combination of lenses, and the combination is such that if you have f1 and f2 for a compound lens containing two lenses, and the two lenses can be a combination of a convex biconvex lens and a biconcave lens with focal length f1 and f2. So if you keep them very close to each other such that the combination can be called a compound lens, then the effective focal length of that compound lens is simply given by this equation, 1 by f equals 1 by f1 plus 1 by f2. And here the f1 and f2 have to be taken with proper sign convention, meaning for biconvex lens it is positive and for biconcave lens it has to be negative. The mirrors and the lenses that we talked about are primarily the most commonly found elements, optical elements, which are used in any kind of optical instrument. For example, camera, which is an amazing device and that everybody uses these days. The camera may contain 2 or more lenses, plus mirrors and plus a screen to record or to save the image. So a lens is nothing but an optical device that creates a Fourier transform of the object placed in the object plane onto a corresponding image in the image plane, and the Fourier transform created by the lens can be written as shown here, capital UI, which is the pattern that is created by the lens in the image plane, a function of variables u and v from the center of the plane, is proportional to a function called impulse response by the lens, that is h, which is dependent on the variables in the image plane uv and the variables in the object plane xy, times an operator u0 that is used to define the object in the object plane and is a function of coordinates x and y. So you take the Fourier transform of this function u0 or this operator along with the impulse function h, and you get the image in the image plane created by the lens. In the classical wave nature of light, like any other classical waves such as sound waves, waves on water surface, the light waves have a wavelength and they travel with a certain speed in a medium. It is composed of various kinds of colors. In the visible part of the electromagnetic spectrum that we can see with our eyes, we have colors from red to blue, and the wavelength of red is larger than the wavelength of the blue light. And the phenomena which we can explain by using the wave nature of light are such as interference or diffraction of light. And these two pictures shown on the left are explaining the interference of light waves. So now, after having the idea that light can be considered as a collection of classical waves, we talk about electromagnetic spectrum. So we say that light is nothing but collection of electromagnetic waves, but these waves, the light that we know, that is visible light, is only a fraction, is only a tiny part of a large electromagnetic spectrum which spans from electromagnetic waves which have a large or very long wavelength, that is radio waves, to electromagnetic waves which have very short wavelength, such as cosmic rays. So this whole spectrum is called the electromagnetic spectrum, and we should keep in mind that our visible spectrum or the light spectrum that we know is only a fraction, a tiny fraction of this big electromagnetic spectrum. In terms of wavelengths, the visible light spans from a wavelength around 350 nanometers to around 750 nanometer. Maxwell's electromagnetic waves. So the electromagnetic waves, either the radio waves or the cosmic rays, all these electromagnetic waves can be very well described by the Maxwell's theory, and the light we know, that is the visible light, are transverse waves according to the Maxwell's theory, which says that if the light is propagating or the electromagnetic waves are propagating in a direction defined by a vector k. Then the light is composed of electric and magnetic vectors, magnetic field vectors, and these vectors are oscillating in a plane which is perpendicular to the direction of the propagation. And the plane wave solutions of the Maxwell's equations can be written down as, for the electric field, E equals some kind of amplitude E0 times a sinusoidal pattern which depends on the spatial coordinate z times the magnitude of the propagation vector k minus omega t. Omega is the angular frequency of the wave. Similarly, for the magnetic field component, B equals amplitude B0 times sine kz minus omega t. And for electromagnetic waves, according to Maxwell's theory, the speed of the waves, that is c, is equals the amplitude E0 divided by the amplitude B0. So the thing that we learned from this slide is that the magnetic field component of light or electromagnetic waves is very much smaller than the amplitude of the electric field component, and that is E0 divided by c. Maxwell's equation, there are 4 equations which were written down by Maxwell about 150 years ago, and these are as the following. The first equation is about divergence of electric field, and if there is a free charge density in that medium, then divergence of E is equals the free charge density. The second equation is curl of electric field is a negative time derivative of the magnetic field component. Third equation is divergence of magnetic field in any medium is equal to 0. The fourth equation is about curl of the magnetic field vector equals mu, which is the magnetic permeability, times epsilon, which is electric permittivity, times the time derivative of the magnetic field. So in free space, these Maxwell's equations can be reduced to simpler forms. The first equation is del dot E equals 0 in absence of any free charge density. The second equation is curl of E equals minus del B by del T. Third equation del dot B equals 0. Fourth equation del cross B equals mu naught times epsilon naught times del E by del T, where mu naught and epsilon naught are the corresponding magnetic permeability and electric permittivity of the free space. Now from the 4 Maxwell's equations, a wave equation called electromagnetic wave equation can be readily derived, and that for the electric field component is del square E equals mu naught times epsilon naught times double derivative of the electric field component. Similarly, for the magnetic field component, del square B equals mu naught times epsilon naught times double time derivative of the magnetic field component. And the generic solutions, which we pointed out before also, of these wave equations for the electric and magnetic field components are sinusoidal solutions, plane wave solutions we call them. So E equals E naught, which is amplitude of the electric field component, times sine kz minus omega t. More generalized notation, it can be written in the form of complex notations, where E equals real part of E naught e to the power I kz minus omega t, and similarly for the magnetic field component. Let's chalk down some of the basic properties of these electromagnetic waves or the Maxwell's electromagnetic waves. The first one is that the time derivative of electric fields always produce magnetic fields and vice versa. That is what we have learned from the Maxwell's equation, which is true for all kinds of electromagnetic waves. The second point is the direction of the electric and magnetic field vectors are always perpendicular to the wave vector k. Vector dot products E dot k and B dot k are always 0 for all the electromagnetic waves that we know. And the vector cross product E cross B is always in the direction of the wave vector k. Third point is the magnetic field vector is perpendicular to both the electric field vector E and the propagation vector k. That is, the cross product k between k and E is always in the direction of the magnetic field vector B. Fourth point is the electric and magnetic field waves in the far field, meaning sufficiently far from the source. So the electric and magnetic field waves in the far field travel at the speed of light, which is denoted by c, and in free space we already have pointed that out, that it is 3 into 10 to the power 8 meters per second. Another property of electromagnetic waves is that the direction of electromagnetic energy propagation is given by a vector called Poynting vector, and that is given by B times E divided by C. Another important property of electromagnetic waves is the intensity, and that quantifies the amount of light or amount of electromagnetic waves propagating through space or any medium, and which is given by I equals electric field amplitude square, and it is measured in terms of watts per meter square. As we pointed out before also, polarization is very important characteristic of electromagnetic waves that defines the direction of oscillations of the electric field component of the electromagnetic waves. So the polarization of electromagnetic waves can be either linear, it can be circular or elliptical. As shown in this picture here, we have all these three cases presented very well. In the first picture, that is A, we have the light propagating in the direction Z, and we have the electric field vector E in the direction X, and we have the magnetic field vector B in the direction Y. So the vector E, the amplitude of that vector is oscillating in the plane XZ, and it remains in that plane. So this is linearly polarized light, or more specifically, this is X linearly polarized, X-axis linearly polarized light. In the picture B, in the same fashion, we have again the same picture which was shown in A, but here we are not showing the B component of the light, and here we are showing only the electric field component, and the electric field component is oscillating in the XZ plane. So this is X polarized light. In the picture C, we have Y polarized light, and in the picture D, we have a circularly polarized light, meaning the electric field component of the light is oscillating always in a plane which is perpendicular to the direction Z of propagation of light or electromagnetic waves, but the oscillation of the electric field is such that if you look from any XY plane, it appears to be a circle or an ellipse on the screen. So this is the example of an elliptically polarized light, and circular polarization is very special case of the elliptical polarization. So here now we are going to talk about polarizers, Polaroids. What are these devices? These devices are very special devices which are used to either polarize the light, the unpolarized light, or to detect the polarization of the light. So in this picture shown here, if you have unpolarized light coming from some source and you put a polarizer in front of it, the light passing through the polarizer will have a polarization axis that is parallel to the axis, the polarization axis of the polarizer. So if you have a linear polarizer, you obtain linearly polarized light. Similarly, if you want to detect the polarization axis of the linearly polarized light, you need to use two polarizers as shown in figure B and C here. So in front of the source you put one polarizer that ensures that you get polarized light, and use another polarizer that is called analyzer, and the polarization axis of the analyzer is such that it is perpendicular to the polarization axis of the light transmitted through the first polarizer. So in principle, you should not see any light coming through the second polarizer or coming through the analyzer when the axes of the two polarizers are perpendicular to each other. And this is how you can analyze the polarization axis of the light. Let's continue our discussion with the wave nature of light or wave nature of the electromagnetic radiation. We talk about interference here. So in this one, the first example that comes to mind is the Young's double slit experiment, in which you have light coming from light source in the form of spherical waves, and you put a screen which has two slits, S1 and S2, and these slits can be of two types. One, a circular slit, so they are represented as S1 and S2, for example in this picture. So the slits can be either circular in shape, or they can be rectangular, in which they are extended along one direction and light is propagating along Z direction. So on a screen placed at the far field, what do you expect? You generally expect that the light which should pass through the slits should just have the same kind of size what the slits had. But what in reality we observe is not single light patterns on the screen, but there is a kind of dark and bright fringes making a nice pattern on the screen. And the reason why this pattern comes on the screen is because of the property of interference of light waves. So interference is the example actually which strongly supports the wave nature of light. So if you had circular slits, you see a pattern on the screen as shown in figure B here. If the slits were rectangular in shape, extended along the direction which is perpendicular to the plane of this light, then you expect and actually you see a kind of pattern which is shown here in figure 3. Consider not two slits but just one slit, either a rectangular slit or a circular hole. Classically, if you shine the slit or the hole with light which is plane wave, you just expect a single dot or single rectangular light pattern on the screen, but that doesn't happen in reality. What actually you see on the screen in the far field, you see a pattern, nice pattern. So you see a strong, a very intense pattern of light in the center, and then around that you see a nice pattern, and that pattern is created by interference between light waves getting diffracted from various corners of the slit or the circular aperture. So the intensity at the center is the maximum, and it appears to be as shown here in the figure, in the middle figure. So for circular aperture, the pattern appears to be made of circular fringes as shown here, and for the rectangular aperture or rectangular slit, depending on in which direction the slit is extended, you don't expect or you don't see any kind of pattern, but in the direction of the width of the slit you see a nice diffraction pattern. Let's understand it further. What happens? What is diffraction by a rectangular or a square slit? As shown in this picture here, light is shined or incident upon the aperture which has dimensions a and b along x and y directions, and the pattern you see on the screen looks like this. So if the dimensions of the slit a and b are such that these are comparable with the wavelength of the light that is used, so you must see a diffraction pattern along both the directions x and y. In the last slide, we considered an example where the rectangular slit was such that only along the width of the slit, the size was comparable to the wavelength, whereas along the length of the slit, the size of the aperture was much larger than the wavelength of light. So we did not see any diffraction pattern along the length of the slit, but we saw a diffraction pattern along the width of the slit. So here we have the slit which is rectangular in shape, but again we have the two dimensions of the slit comparable with the wavelength of light, and therefore we have a diffraction pattern by the slit created along both of its dimensions, meaning both along x and y. So if the slit is rectangular, you see different sizes of the maxima and minima pattern on the screen. If the slit was square in shape, then you get a symmetric pattern on the screen. This property of diffraction of light from slits is very well used in applications or in devices, and one of these devices is called diffraction grating, which is nothing but a combination of an infinite or a large number of such slits. So every slit is diffracting light, so a combination of slits also diffracts light in such a way that on the screen you get the colors separated. Different color in the incident light gets scattered in a different direction. So diffraction gratings are used to separate the colors, and ability of diffraction gratings to separate the colors is called resolving power. And if R can be represented as the resolving power of a grating, then it is lambda divided by delta lambda, where lambda is the wavelength which we want to resolve and delta lambda is the separation between this wavelength and the next wavelength that can be resolved. And this resolving power depends on the number of slits in the grating and times the order of diffraction. Generally, the diffraction equation for a grating is written as d times sine theta equals m lambda, where m is a number, an integer, which is the order of diffraction. It can be from 0 to infinity. Lambda is the wavelength and theta is the angle of diffraction. So depending on the order of diffraction, the theta varies, the angle varies. And d is the grating period, meaning the separation between two slits in the grating. There is another optical element which is used for separating colors in the space, and that is called a prism. So prism is a device which, because of its dispersion property, is able to separate all the wavelengths present in white light, for example. As shown in this picture here, you have an incident beam which contains, let's say, two wavelengths, lambda and lambda plus delta lambda, and delta lambda is the separation between the two wavelengths. And if you are able to separate the two wavelengths, then that defines the resolving power of the prism. And in this particular example, it depends on the thickness of the prism and the dispersion. Dispersion is nothing but the refractive index of the medium of the prism versus the wavelength of light. So not for every color, not for every wavelength of light, the refractive index of the medium is the same. It varies as a function of the wavelength. That is called dispersion property of the medium. And depending on dn by d lambda, that is the dispersion of the prism material, you get a very specific value for the resolving power of the prism. So prism is similar to the grating, another device that is used for resolving wavelengths, very nearby wavelengths. Now let's talk about the quantum nature of light. So far we were discussing about the geometrical optics, that is how images are created or how plane mirrors or curved mirrors or lenses work and so on. Then we discussed about the wave properties of light, where we assume the light or the electromagnetic radiation as classical waves. We defined a wavelength. we defined a speed of wave propagation and so on, and we explained the electromagnetic waves through Maxwell's equations and the wave equation, and then we were able to explain the interference and diffraction phenomena. Now here there are some phenomena in nature which cannot be explained by simply considering the geometrical optics or the wave nature of light. We need more than that, and that is the description of light by in terms of quantum particles, and they are photons. So now light is made of photons, and photons are nothing but quantum particles or quanta of energy, meaning these are packets of energy. So now we have to learn light in terms of particles or photons. Description of light is very important because only this nature of light can explain certain phenomena in light. First of such phenomena is the photoelectric effect, for which Einstein got Nobel Prize in the 20th century, in the beginning of 20th century. So he described an optical phenomena in which you shine light on some metal surface or some material, and electrons are ejected out from the surface of the material. And depending on the color or the frequency of the light that is shined on the surface, you have different kinetic energy of these electrons. So the kinetic energy of the electrons was not dependent on the intensity, rather it was dependent on the color or the frequency of the incident light. This was not explained properly without the help of Einstein's quantum light picture, where he considered light made of photons, and each photon strikes out a fraction of electron, or that is called quantum efficiency. You shine in 100 photons and few electrons are ejected out, and the kinetic energy depends on the frequency of that photon, not the number of photons. So we need the quantum nature of light to explain, for example, photoelectric effect, and then we will come to scattering. Scattering is another phenomenon where quantum nature of light is needed to explain. As we said just now, that scattering is another phenomenon for which we need the quantum nature of light for a proper explanation. And the scattering is nothing but you shine in some photons on some material, and the photons get scattered, and in the process the material, which is composed of particles again, it gets recoiled. And the first of such kind of experiment was given by Compton for X-rays photons. So he shined in X-ray photons on electrons, and electrons got recoiled, and the photons which were incident on the electrons got scattered in a different direction. So depending on the energy of the scattered X-ray photons and their direction, the direction of the electron recoiled or vice versa can be estimated. So this kind of scattering of X-ray photons from electrons in any material was seen for the first time by Compton, and this is called Compton scattering of X-ray photons. And the scattering, the way it occurs, can be elastic in nature or inelastic. Elastic means there is no change in the energy of the incident photons, and in the inelastic scattering process there is a change in the energy, meaning there is energy exchange between the incident photons and the material particles with which the photons are scattering or interacting. And the scattering processes can be of various types. Rayleigh scattering is an example of elastic scattering, where incident and the scattered light has the same energy. Raman scattering is another very important scattering process for which our Indian scientist Professor C.V. Raman got Nobel Prize in year 1928 or so. Compton scattering, as we just explained, is another scattering process, and then we have Brillouin scattering. So scattering is a process which, for a proper explanation, need to be explained properly by the help of the quantum nature of light. The most fascinating discovery of the last century was the invention of laser, which means light amplification by stimulated emission, and a laser is the source of intense light. Generally, the light which we have got from natural sources of light, or the sources which we have commonly used in our houses, they do not produce light which is intense enough. But laser is a source where we can produce very intense light, and that too at our will. So what is a laser? Laser is nothing but a cavity made of plane mirrors or curved mirrors, and a gain medium which is pumped externally to achieve population inversion. And once you have the photons inside the cavity, they basically make a laser beam. And the laser beam, the simplest way to understand it, is a constructive interference of various waves which are propagating inside the cavity. And when you have constructive interference, the amplitudes of various waves add up and give you a resultant wave which is very intense. So the lower diagram in this slide is to explain the lasing phenomenon. What happens here? You have some kind of optical pumping of the gain medium. In this particular example, it is happening through optical pumping, meaning you have some incident photons and they excite the gain medium. Because of the optical excitation, you have the population build up in the excited state. But that is not the label which is lasing. You need to have a label which has high lifetime for lasing. And that is the label which is represented as E3 here. So the population builds up, takes some time in the excited state 3 with energy E3, and then the population decays from this label to the ground state, and in the decay process, whenever there is an incident photon available having the same frequency, will have not only the same frequency but also phase and direction of emission, and that is how we will get a coherent beam of light coming out from the laser. So the lasers are available in various forms. They can be continuous lasers, meaning the light output from the laser is continuously available as a function of time. The output of lasers can be in the form of pulses, meaning you get the energy, the light energy in the form of pulses. There are lasers which are called as low power lasers, and there are lasers which are called high power lasers. So the demarcation line for them is such that low power lasers are not harmful for your skin or for your eyes, but high power lasers, beyond a certain intensity level, every laser is termed as a high power laser, which one has to be very careful in handling to avoid damages and so on. Here there are some review questions for you to help you understand how far or how much you have learned from this module. The first question is that we put here is, we ask, can Maxwell's equation be derived? The second question we ask is, the electric field of a circularly polarized light vibrates in the direction of light propagation. Is this statement true or false? Third question that we ask is whether laser is a coherent source of light or not. Other two quick questions for a review. The first, in free space, electric field vector of light is given by E equals E naught times sine of 3 times 10 to the power 6 Z minus omega t. Estimate or calculate the frequency of this light. The last question for review, is, consider a square slit of dimension A equals 0.01 centimeter. For light of wavelength lambda equals 500 nanometer, draw the diffraction pattern on a screen placed at distance d equals 100 centimeter from the plane of the slit. So students, let's summarize what we have learned in this module. We have learned that light that we see is only a small fraction of a large electromagnetic spectrum, which spans from waves having very large wavelength such as radio waves to waves having very short wavelength such as cosmic rays. The electromagnetic waves have oscillating electric and magnetic fields in the transverse plane to the direction of the light propagation. Geometrical ray optics is useful in most of the optical instrumentation related to spectroscopy and imaging. We also learned that light has not only the wave nature, but it has quantum particle nature as well, which is useful in explaining certain optical phenomena. What are those optical phenomena? Like scattering and photoelectric effect. In most of the optical instruments, we would find optical elements such as mirrors, lenses, gratings and prisms. All these have been covered in this current module to an extent that is quite reasonable to know of them. Laser is one of the most fascinating discoveries of the last century, which has revolutionized the field of optics. Lasers are being used everywhere these days for all kinds of applications, including biological applications.